Our first speaker in the hardware session is Mike Houston. So Mike has a PhD from Stanford University and is an AMD fellow, and most recently, the chief architect for server APUs. Mike was one of the earlier researchers in GPUs and led AMD's GPU compute efforts in hardware and software, and is now one of the overall leads for heterogeneous computing at AMD. Mike?
Thanks, Dana. So let's see if the technology will work for me. OK, so I'm going to talk about heterogeneous computing and actually two forms of it. Sort of the chip-level heterogeneous computing, I'll spend the first part on, and then system-level heterogeneous computing. So AMD acquired a company earlier in the year called C-Micro, and so I'll discuss some of those solutions and why it may be interesting for this community. So for this slide, many people in this room have probably seen things of this nature before. So Chuck Moore and I put this together for a presentation a few years ago. So if you look at where we came from, even not that long ago, it was a single-core era. Right? We got all performance increases, memory bandwidth increases, sort of general increases across application performance, enabled by Moore's law and voltage scaling. So this allowed us to, with voltage scaling, increase frequencies. Right? Now, we obviously hit a wall. Right? We're not sitting around all running on 15 gigahertz CPUs today, although there were people even 10 years ago that really thought that's where we were going to be. As a matter of fact, we're actually taking away CPU performance now as an industry. Right? We're actually not increasing it. And there's a couple things that are causing that to happen. So to increase performance of single core, you get constrained by power and complexity. Right? I mean, AMD and Intel build some of the most macho, out-of-order cores possible. Right? IBM as well. But we've hit limits on where we can go with complexity and power. The other thing is trends overall in the industry, both in consumer and in high-end server, are shifting to incredibly power-constrained environments. So that shifts where we focus. So the entire industry moved to going to multi-core. Right? If we can't make a single core faster, well, let's just stamp out more on a chip. But some interesting things are happening there. So again, we were able to take advantage of Moore's law. So as transistor densities increased, we would stamp out more cores. We moved to SMP architectures. We kind of got software people over to deal with SMP. As soon as you start dealing with like NUMA-like systems, basically software all fell apart on us. But we continue to hit the same walls. So you hit walls in power. You actually hit walls in complexity. We can only scale out so large until things like cache coherence protocols get in the way. And there's also physical design limit issues. Parallel software, huge issue. As I said, NUMA, there's very few people in the world that can actually effectively code for a NUMA system. And that's fairly easy to where the industry is going. I'll show you some examples of where we're going. Things are about to get hard real fast. And then we hit the scalability limit. So you can argue, if it's 32 cores, 64 cores, but you guys can buy 64-core machines today, and that's really about the limit of how big we can build a system. So where do we go now? So the entire system is now moving to heterogeneous systems. So everybody has a heterogeneous system with them today, either in your pocket in the form of a cell phone or your laptop. Right? So a heterogeneous system combines multiple different types of cores. So classic way you generally think about things in the consumer space is a CPU and a GPU combined together on the same die. Right? So AMD and Intel in the major high-end consumer space actually ship these. So Ivy Bridge from Intel or AMD's Trinity chip. In the cell phone space, right, every ARM design you've ever seen, so NVIDIA Tegra, if you have a Xenos chip, any of the Samsung chips, the brand new iPhone 5, right, that's an A6 chip, those are all heterogeneous chips, CPUs, GPUs. But what's also interesting is all those chips, including the embedded cell phone chips, also include other forms of accelerators. So we have application-specific accelerators. So video encode logic, video decode logic, DSPs for audio processing. Our chips have fixed function encode and decode engine, encrypt and decrypt engine, so we can do line rate AES encryption on our chips. There's people that, so Freescale builds chips that have data compressors and decompressors on die. So we're starting to see this big shift towards combining multiple cores together to give the best optimized experience for a given set of workloads. Okay. So if you look at GPUs, GPUs are really targeted to go after sort of big flat data parallels. So think image and video processing. That's really where GPUs really dominate from a compute point of view. but also show you some other surprising examples like Memcache D. As it turns out, a GPU can do extremely well. But there's lots of issues with this. Remember how I said that we were going to take the multi-core era and we were going to make it even harder on programmers. So the programming models for these types of systems are very difficult to deal with, right? So there's a standard called OpenCL. It's usable, but it's very hard, right? It was never designed for your average programmer. It was designed for other languages to be built on top of it. Things like Java, right? Things like Hadoop. So we'll talk about those a little bit later. So on the software side, another way to think about this is in the dark ages of CPUs, we really did code and assembly. Then we moved to slightly more sanity, C and C++, and then on to things like Java, JavaScript, Python, PHP, Perl, et cetera. Multicore era, we went through a similar thing. I mean, pthreads is like the assembly level equivalent of dealing with threads, but then we moved to things like OpenMP, TBB, other sort of parallel runtime systems to manage threads. For heterogeneous systems, especially when dealing with the GPU, we used to actually code these things when I was in grad school using graphics APIs. You would literally draw triangles to do computation. Come a long way. So you have C-looking things like CUDA and OpenCL. But again, if that's where things stop, then these chips will all fail, right? They're too hard to use for the general programmer. So we have to fix that. So another way to think about why this trend has happened is if you look at the client market. So remember, the client market fundamentally drives everything, right? Server, even big data is a blip in total attainable market compared to client. But if you look in client, the main workloads we deal with are video and image processing, right? The problem is we actually run most of this code on CPUs which are designed for scalar workloads, things that branch a lot, things that have hard latency requirements. But they're really not efficient. You actually waste a lot of power running on these cores compared to the other cores in a heterogeneous system. So AMD has worked with a bunch of other industry folks to start something called the Heterogeneous System Architecture. So it's a foundation. I'll show you the member list in a second. But it's an open architecture. This is really sort of an architecture that's a platform level. It sits below things like OpenCL. It's what is the industry going to commit to in terms of capabilities to make software easier to program. So there's three main parts of this. You can look up more information on the web. But there's a virtual ISA. So compilers actually target a virtual ISA. Think Java bytecode in your mind, but it's actually lower than that. There's actually full register allocation that's actually done, instruction scheduling at this level. So it really is a virtual ISA. We can do near linear time translation into the actual machine ISA. There's a memory model. So we now have a consistent memory model. It's based off of C++11. It's very similar, actually, to the Java model as well, but that's now guaranteed across all the vendors that support HSA. So this tells you how you can communicate and what the rules are between dealing with your main CPU cores and all the accelerators in your system, right? So it provides sanity to that. To sum up, it's a relaxed consistency model. And then a standard way to now dispatch to devices. How do I send this work to that device, and how do I give it the pointer for the data that's going to be dealing with? So it's ISA agnostic. So in the case of AMD, so we can run the same HSAL on either the CPU or the GPU. You can also run on FPGAs, ARM cores, Imagination GPUs, et cetera, right? Or run on anything. And so we're inviting folks to join us, and there's a whole academic track, and there's lots of specifics I can talk to you later about if people are interested. But if you look at who's coming together to do this, so we have a lot of players in the industry. So AMD and ARM were the first two. Imagination, MediaTek, Samsung, and TI, right? So most of the folks are currently embedded, and because heterogeneous computing makes the most sense right now in embedded. That's what we've already figured out as an industry. So there will be more people you'll see showing up from other areas like the server market. So what are the basic goals of HSA, and more specifically, why AMD is building Fusion chips? So we want to actually make all the processing capabilities of an APU, so CPU and GPU, available to the average programmer. So to give you an idea, our current Trinity chip is capable of 768 gigaflops in 35 watts. All right, it's the highest compute density you can get. It actually rivals many FPGAs in terms of overall compute density. In terms of hashing performance, it'll hold its own against even the highest end Vertex cores. To be successful, we have to dramatically expand how many people can actually code for APUs. And our main focus is to enable both sides of the pipe. meaning to enable everything that happens on the back end of server, and then everything that happens in your hand, right? The whole world is moving to the cloud, the mythical buzzword cloud. Okay, so what is an APU? So AMD is actually on our 2nd generation APU. We build APUs in all power segments now, all the way from 5 watts all the way up to 125 watts. We combine the scalar processing capabilities of the CPU, so classic big iron x86 CPU, with the parallel processing high throughput designs of a GPU core. And they both share the same memory system, same memory controller. So fundamentally, you're not DMAing data back and forth between the CPU and the GPU, which often actually kills GPU accelerated performance. So in terms of architectural roadmap, so this may sound subtle, but the actual silicon commitment to do this is quite high. But this is required to actually make things work. So last year was when we introduced our first Fusion cores. So this is when we integrated CPU and GPU on the same piece of silicon. Okay, why does that matter? It allows us to use a unified memory controller. Why does that matter? It allows you to not move the data. The CPU can malloc an array. On current GPUs, I then pin it, and the GPU touches it directly. That PCIe bus will kill you in terms of data transfer, and I'll show you some interesting data on Memcache D. Normally, you don't think Memcache D is going to run well on a GPU. It's because the PCIe bus is in the way. If I remove the PCIe bus, a GPU is actually dominant on Memcache D. 2012, so we've increased our capabilities of our GPU cores so we can deal with languages like C++. So we're much more flexible in what our GPU cores are capable of. We've now moved to a lower dispatch scheduling mechanism. Instead of having to go through kernel crossings to dispatch, we can actually dispatch from user space. So instead of taking 50 microseconds to dispatch a packet, we're actually sub 7 microseconds now on most systems. The other thing we did on the APU is we implemented bidirectional power management. So we can shift up to 80% of the power to one side of the chip or the other. I.e., if you're running a GPU-intensive workload, we can shift 80% of the power to the GPU, run it at the highest frequencies we can, and then slow down the CPU, and vice versa. Right? So you're not paying that much power overhead if you're not using the cores that you're on. It seems kind of obvious. Silicon to pull that off is challenging. So moving to next year is where we take the big leap, and this is technically our first HSA chip. So we move to a true unified address space. What this means, I can pass an x86 pointer to the GPU and it can use it directly. All page table protection, page fault, everything. Basically, the CPU now has the exact same capabilities memory-wise, or the GPU has the exact same capabilities memory-wise as the CPU does. This changes things a lot. It means if you have nested data structures, linked lists, things with pointers, instead of trying to package it up and trying to download it to the GPU, you touch it directly. Raw malloc memory directly. We also gain full coherence. So that means I can do data structure builds on the CPU, which the GPU is not good at, but then actually pound through all the data on the GPU and have those actually have the same view of memory at all time. So I can implement things like locks between the CPU and the GPU, semaphores, general atomics, right? Everything works between the CPU and the GPU. Then as we move forward, it's probably less interesting to this group, but we get the rest of sort of the features. So we moved the capability to do rapid context switch. So we can actually have multiple simultaneous users protected by VMs running together on the same chip. So for general server workloads, especially for virtualization, this is quite important. OK, so let's talk about Memcache D. So usually when people think about GPUs, they say, yeah, it's a floating point engine. That's all it's good at. Well, GPUs are actually also the fastest integer engines in the world as well. So if you go look at the Bitcoin mining numbers, just pretend that that's not used for nasty things. AMD actually is one of the highest ranked in terms of processors. And again, it's because we actually have special optimizations to implement high-speed hashing and encryption. Okay? So it's important for Memcache D because you spend a lot of your time hashing. So you guys all know what this is, so I'm actually going to skip this slide. But it's a distributed object tracking system, used lots of places. So here's the raw data. So that multi-threaded CPU is a Sandy Bridge Xeon. You notice our discrete GPU is not doing well. Right? This is usually where academics end and say, GPUs suck. Look how fast our APUs are doing. So Trinity is our brand new one. Zacate is our little tiny low power one that runs a Bobcat core, for those that know what it is, from a while ago. So they're actually outrunning a high-end Xeon core. So you start to get a little surprised. So let's look at where we're actually spending our time. So on the CPU, you don't have any data transfer, so it's all execution time. the reason the discrete GPU gets killed, and the reason that most applications actually don't get that much speed up on a discrete GPU, is you're spending all your time doing data transfer. The compute's insanely fast, right? But when you take a look at actual application performance, not just the kernel performance that people like to publish in papers, it's really challenged. But if you go to the APUs, what's interesting is that blue mark, remember I said we have to create these dispatch packets? That's the extra data transfer for dispatch packets. You notice that Trinity is actually spending most of its time executing. So you get almost all the benefit of the GPU running this application. So why is Memcache D fast on an APU? Very fast hashing, okay? And if you think about high-load Memcache D, GPUs have thousands of threads running, which means we're capable of responding to very high load, okay? Now, to be fair, what's not discussed here is many Memcache D workloads are I/O bound, network stack bound, right? So there always are caveats. So in this case, we're actually running very, very heavy on the Memcache D side to negate the network impact. Okay. Another thing is accelerating Java. So we're working actually with a few folks to actually get GPU accelerated Hadoop up. It's one of the reasons we invested in Java. So let me explain sort of how this works. So write your Java source code as normal, no special tricks. Use a standard compiler, no special tricks. Package it standard way, no special tricks. So what you actually end up doing is you change what you extend. So instead of extending the run method on Java thread, you extend the run method on Java kernel, right? You basically now pull in an AMD library. When you pull in our library, we on the fly, at runtime, convert bytecode into OpenCL code and execute it on the GPU, right? So you haven't written any OpenCL code, it's all Java code. And it'll actually execute on any OpenCL device. This will run on NVIDIA, it'll run on Intel, just fine. So if it can't find an OpenCL implementation, and not every loop in the world can we translate to OpenCL, it'll go back to a fallback path. The other interesting thing is that against many JVMs, the thread pool implementation that we have is actually faster, so people are even seeing speedups just using this. So the way this actually works, so you have your application, you have the JVM, you pull in the apparappy runtime. Right? JVM runs as normal. We do our intercept and submit separately to OpenCL. So go forward, we'll actually end up switching from OpenCL to HSAL. There's some weird policy issues in OpenCL that currently reduce performance. We can bypass by going lower than OpenCL to HSA. Then we begin effectively doing hotspot analysis on our own. And if people saw the announcement between AMD and Oracle, we'll actually move this into the JVM. So the JVM itself will begin to understand heterogeneous computing. So apparappy is being slated to go into the next version of Java as well as the OpenJDK. So for people that program a lot of Java, especially a lot of Hadoop developers, this begins to get kind of interesting. So we have a couple of research projects with a couple of labs that are actually doing OpenCL accelerated Hadoop using this path, exactly. Talk about software stacks for a little bit. So one of the pains of programming OpenCL or C++ AMP is there isn't a standard template library. So AMD is open sourcing what we call Bolt. So it has common data parallel functions, scan, sort, reduce, transform, a bunch of the things that you need, as well as a bunch of data structures, parallel hash maps, things like that. So we'll have an OpenCL and C++ AMP version that will be open source. So you get to use all the happiness, the HSA platform, and sort of sum up the HSA platform, you move the computation, not the data, right? All your power in a system is moving the data. Computation, power-wise, is basically free now. It's orders of magnitude cheaper than putting something in DRAM. And Bolt gives you, besides the Java way of doing single source, Bolt also now gives you a single source way to do it. So it relieves some of the pain of OpenCL. So from a stack point of view, here's basically what it looks like. So for those who have seen driver pictures before of how the Windows driver works or the Linux driver works, this is somewhat similar. So if you look at the OpenCL runtime, for example, instead of using our current driver path, this will be implemented on top of the HSA runtime, which will have access to this compiler, the HSA finalizer, as well as a kernel driver. What's interesting, though, is once you actually bootstrap and compile your code, the application begins submitting directly to the hardware. There's no kernel mode crossings. There's no other runtime. Right? You can submit directly to the hardware. So it removes a lot of cruft. So all this will actually be open sourcing of our stack. Now, it takes a surprisingly long time to actually get everything out and upstream in Linux, but we're already beginning to push. So we'll have a kernel driver that's open. It's not interesting to anybody else because it's specific to our hardware. We have a finalizer. Again, it'll be open, but specific to our hardware. But there'll be a runtime that will work across any HSA implementation. Again, that's a platform architected commitment from the foundation. An assembler will be contributing all our LLVM optimization work and code generation for HSAIL back to the LLVM community. We'll actually open our OpenCL compiler in runtime. So it'll be consistent across any HSA implementation, and then we'll be opening Bolt. So let me switch gears for a second. So that was sort of, OK, what do we do on a chip? Okay, now let's talk about what does the system look like. So AMD acquired a startup called C-Micro. So C-Micro specializes in ultra-high dense computing. So thankfully, they just announced this yesterday, so I can actually talk about it publicly. So they released their 15,000 product family. To give you kind of an overview of the densities we're talking about, then I'll get into the more interesting stuff on how many disks we can actually put behind this thing and how it's virtualized. So it's a 10U. We can put 16 servers into 10U. I'll show you a little bit more information on the interconnect, but it's a 3D torus. It's actually an 8 cube. 1.28 terabit per second fabric interconnect. We can get 160 gigi uplink off of this thing. We can put 64 internal drives or up to 1,344 external drives, so people can start doing the math. 5 petabyte that can attach to this thing. Hardware RAID, hot swappable, and it's actually hardware virtualized. There's actually a special ASIC chip that connects to the fabric. So you can actually use all this with off-the-shelf operating systems and VMs, no modification. It's actually silicon that does all the I/O virtualization in the system. So here's sort of what a server blade looks like. So this is the latest Opteron blade. So on one of these blades, we can put an 8-core Opteron. There's various SKUs that you can buy. But another way to think about this is I can put 512 cores in a 10U or 2K cores in a rack. Each one of these cards can do 64 gigs of ECC. So again, if you're doing the math, 4 terabytes in a 10U, 16 terabytes in a rack. And then there's 8 by 1 gig per server node. So through the storage enclosures, this is the things that are external that can connect into the fabric. So that 1.28 terabit per second, I can connect the disks via that fabric. So if you go to the highest capacity node, it means I can scale out to 5.3 petabyte using 4 terabyte drives. Again, this can all be sitting happily in RAID. And then we have the lower cost variants. So if you look at the interconnect, so it's an 8 cube. So it's 1.28 terabits per second bandwidth, and it's 0.5 microseconds per hop. So end-to-end, corner-to-corner ends up being 6 microseconds. I can hotplug various forms of network I/O. And yes, I did say hotplug. Again, there's hardware virtualization that will deal with the rerouting. So I can switch out 10 gig, 1 gig, and leave the system up. And same thing with disk. I can hotplug disk. And because everything is being virtualized, all these things just look like a SATA controller to each of the nodes. Right? The disks just look like a giant disk back behind things to each of the nodes. The other interesting thing is I can soft partition. So I can guarantee, quality of service-wise, a certain amount of disk space, a certain amount of bandwidth, both to the disk, both to the network, to each node. So it's a very flexible system. So again, if you begin sort of pulling this thing out, so this becomes the base building block, right? One of these 10U enclosures, chock full of cores. So 2,000 cores in a rack, 4 terabytes in a system. And so if you think about it from a pure disk point of view, right, for this crowd specifically. So if you look at what it takes to put 5 petabyte of disk in, right now that would take you 6 racks, 112 2 rack unit, dual socket, Sandy Bridge servers, 12 10 gig switches, 224 power cables, 40 kilowatt. We can do the same thing in 1/3 the space, 2 racks. One of these enclosures with a whole bunch of disks behind it, Again, all the disks are virtualized. Only 38 power cords, half the power, half the price. Right. So it's a very different way to build systems. As opposed to putting disks and network in each of the nodes, we've now virtualized and put the nodes on a fabric and put the storage and the network I/O on the fabric. Right? So it changes how you think about systems. So you can dynamically repartition this thing and change out disks, change out network, and balance for the load that you need. Another way to think about that is that the C microfabric is effectively now a socket. So I showed you the AMD Opteron blades. C micro also sells Intel, Sandy Bridge, and Atom-based blades. And there's no reason we couldn't support an ARM blade. So it means that we can mix and match arbitrarily the architectures that actually go in this node and share all the storage, all the I/O consistently and uniformly across all the nodes. Right, so it's a different way to think about heterogeneous computing at the system level. It becomes an arbitrary fabric that I can plug things into. So that was my last slide. So I will take questions. I know that was quite a different talk than many of the rest.
How do I think about which aspects of that are commodity and which aspects are not? Many of us are in a business where what we really want is the shittiest, crappiest, cheapest stuff and a boatload of it.
Right.
And I smell chrome-plated.
Yeah, so the fabric is obviously proprietary, not commodity. Right, sure. All the disks we use inside those chassis are all commodity. You can run the cheapest crap that you want. Although if you care about your data, I'm a little worried about that. But that's true. Yeah, I mean, the main commodity thing is the NICs that go in the back-end chassis. I mean, there's no reason we couldn't run InfiniBand. There's some driver work to do. And same thing with the disks. Basically, anything that actually goes inside any of the external chassis is commodity. Right? Anything inside is proprietary. Yep. So again, if you go compare this out between most of your white box vendors, we will be cheaper, faster, more reliable. Again, we cut a lot. So that card, people don't really sort of understand this about PCB costs and everything. Just shrinking that down, we save a tremendous amount of money. And also, we increase reliability tremendously. If you notice that we don't have a power supply per node, right? One of the highest failures in large systems is power supplies, right? So we have a redundant array across 64 cards. So again, we've removed a lot of cost, out of the system, but it has made it proprietary in the core of the system.
You said that AppRIP was slated to go into the next version of Java, or are you referring to Java 7 or Java 8?
A variant of AppRIP, and it would be Java 9.
Java 9, oh, okay, so in like 10 years.
Yeah, it's maybe more jaded than I would like, but again, this will go to the OpenJDK sooner than that as base level support, but you can use it now if you want. It's just whether or not you want it integrated and whether or not you want the conversion to GPU code, however you get there, to be hotspotted or not. But it's all usable now. I mean, we have people actually using this in production today.
I have a question. Are you working, I'm here, hello.
Yep.
Are you working closely together with the guys who are making database kernels? That's question one. Because second, you are falling actually in the same pitfall, trying to again optimize Java or any existing language. Well, if you go to the core and you take the hardware, you may come up with completely different solutions.
Right.
Geared at this particular community.
Right, so we're actually doing both. I would actually argue that one of the other pitfalls of going after the bottom is you lose all the programmers at the top. Okay? So the reason we're going after Java is just because when everybody saw OpenCL, we had most of the community barf and say, can't we have Java? And then we said, okay, sure. But again, we're not necessarily going after hardcore optimizations of Java. I mean, it's your data parallel loops are getting offload, and you can use a nice, pretty language. As far as actually going after the bottom level and doing direct optimization, yeah, we do this, right? You can see extensions in our GPUs, extensions in our CPUs, extensions in what the network vendors are doing to optimize certain forms of databases. The other honest part of that, though, specifically to kernels, once you start moving up the stack, is, and it's sort of funny to see let's get consensus on going into a new realm. we cannot build hardware for something until there's enough consensus on how to do one thing. Right? This is why we can build H.264 encoders and decoders, because that's the standard way to do things. It's the same thing. You can argue that we can implement gzip in hardware, not the best compressor, but you could implement gzip in hardware really easy, or any block, pick your favorite block-based compressor. But what's interesting is we get a lot of questions about random number generation. So both Intel and AMD have acceleration for random number generation. But nobody can agree on what the base seed algorithm should be. So it's very difficult to do this. So the more consensus there is, and this is sort of pushing back to you guys, the more consensus there is on, well, this is the way everybody does this, then yeah, we can implement hardware. And ideally, I would want to actually try to put that in fixed function or a limited programmable piece of hardware, because I can make it very low power, very cheap, and very fast. But there has to be agreement on what that algorithm is.
Just was the Memcache D
No, it was
tweaked
stock.
to enable vectorization?
It was stock.
Okay.
Well, ported OpenCL, but no, we did not go out and vectorize it. Right? It was the way that OpenCL works. For people who haven't seen it, is you don't actually code for the vector machine the GPU really is. You pretend that each lane in the GPU is an independent thread. So that's actually literally how it's coded. So it's just coded as 1,000, well, in this case, 4,000 threads.
Hi, yeah, you identified exactly the problem with GPUs in terms of the PCI bus and moving data in and out. But are you going to be able to keep the nice thing about the GPU is it has a really fast memory interface, 140 gigabytes on the NVIDIA chip. So do you lose that capability? And
So the balance is different.
Yeah.
And so GPUs are interesting. So we use very exotic memory systems. So both NVIDIA and AMD run what's called GDDR5 memory. Very wide, actually very high latency memory system, right? So I think our current chip is a little bit faster than NVIDIA. We're at 278 gigabytes per second. The problem is the maximum memory capacity that you can get on GDDR5, because it's a single point memory, sucks. 6 gigs, that's it, call it a day. For what you guys do, that's like, oh, come on, right? So again, it's sort of trade-offs. But the other thing is that the APUs, the GPU on these things is much smaller in comparison to a big GPU, right? So if you're doing big, dense, high-performance compute and your whole world is DGEM, then yeah, a discrete GPU is pretty tough to beat. PCIe doesn't even matter in that case. But if you're doing real applications that are slightly irregular, right, or memory, or latency bound on memory, or you're doing combination data structure build, things that don't fit on the GPU very well, an APU will crush those things, even though it's 1/10 of the raw compute performance. Right? So if you actually compare the compute performance against the bandwidth, an APU is actually a very similar ratio to our big discrete GPUs. But yeah, again, most of our APUs today are sold into the commodity space, which means D3, D4 memories. When things happen, with NVRAM and stacked memory technologies, things are going to change. You'll get a step function. But yeah, memory is going to be our limit for a while, right? Physics sucks, right? It can only push so much bandwidth over so many pins at so much power.
Okay, I think we're out of time if you can find Mike later. So let's thank our speaker again.